Morning, everyone. So yesterday we started looking at a little bit of the math again. We started looking at a special reaction, how water can actually self-ionize. Without the presence of other acids and bases, it can spontaneously form H plus and hydroxide. The key is it forms it in 1-to-1 ratios, so it keeps things neutral. What I'm going to do is I'm going to give you a quick warm-up question, just seeing how we did with the math there. And today what we're going to flesh out a little bit here is if we start looking at actually acids and bases, they're also going to have Kas and Kbs. How can we utilize our tables not only to figure out which one's a stronger acid or stronger base, but also do some calculations with Kw. So just as a quick warm-up here, I want you to state the auto-ionization of water. So just state the equation and the equilibrium expression. So that's sort of like products over reactants. We had called this Kw. And then 2, we're going to need that Kw for later as well, but I'm going to just give you a specific, let's deal with a situation. Let's say I have, I want you to calculate the concentration of H plus and the concentration of OH minus in, let's go 3 molar sodium hydroxide. Okay, I'd encourage you just to pause the video, try it out for yourself. Okay, assuming you've done that, let's have a look. Auto-ionization or self-ionization of water really just means for us, water is our only chemical. So if you totally blank out on your chart, it's actually really far down on this table here. It is on the acid side, so it is going to manage to lose a proton, but you see that the constant value is actually very, very tiny. So we're going to write out here water. This one here is currently a liquid. Equilibrium, it's a weak acid. This is going to end up becoming H plus and OH minus. That is the auto-ionization of water. Water will make sure of it that there's always some H plus and hydroxide left over at equilibrium. The equilibrium expression, at first we wanted to say KEQ, but we're just going to change that here. Well, this is equilibrium for the water equation, so let's call it KW. This one here is going to be products over reactants. It's going to be H plus multiplied by OH minus. And the constant here, I want you to memorize this. The constant is 1 times 10 to the negative 14 at 25 degrees Celsius. All right? So that's a constant. That gives us a nice mathematical link here. Whenever we knew one of them, if I knew H plus, I can punch it through this KW section to find OH minus and vice versa. So case in point here, question number 2. They're asking for calculating H plus, calculating OH minus. Be really careful in these questions here. Just because I say calculate the H plus doesn't suddenly mean acidic. Just like find OH minus doesn't suddenly mean basic. It really depends on what the size of these values are. If the H plus is big, sure, it's acidic. But if the OH minus is big, sure, it's basic. So we actually want to look at the interplay. I want to look at the numbers. Whichever one is bigger will tell me whether it's acidic or basic. We're given this time our solution on top of the water that we have. Water already would have self-ionized. Water would have already have generated a few odd H pluses, a few odd OH minuses. We calculated the number yesterday. The molarity was only 10 to the negative 7 molar. So really, really low concentration, right? Not a lot of it. Most of it sticks around as water. Reactants are favored. And now what we do is we then drop in some 3 molar NaOH. So I drop in some NaOH here. Again, as I tried to allude to yesterday, you're going to save yourself a lot of time. Anytime you're given a chemical, ask yourself, what is this? Is it acid or base? Is it strong or weak? Hint for this section here for part 1 of this acid-base chapter, pretty much we're going to do with strong things. Hey, this one here has the characteristic hydroxide particle, so probably a strong base. So as a strong base, it's a soluble salt here. It one-way arrows, forms sodium ions, forms hydroxide ions. We have dropped in enough so the concentration is 3 molar. That means one-way arrow, 3 molar sodium, spectator ion, 3 molar hydroxide ion gets formed. Even though I typically just show my work like that, it is understood that the NaOH is completely ripped apart for it to just remain as hydroxide. So what I've done to this equilibrium expression, I didn't specify change temperature, so I can imagine that this constant is still true. I took the hydroxide, which used to only be 10 to the negative 7, really, really tiny number, and suddenly I beefed up that number by a lot. I've suddenly made the hydroxide number way higher. For 2 numbers to multiply to give this constant here, I would expect the H plus to drop. And in fact, we can actually calculate that there. So I have my Kw expression here. I usually just still write it out. Kw is the H plus times the hydroxide. Well, the hydroxide is now 3 molar. Yes, you could argue what's 3 molar plus that 0.0001, right? Well, practically 3. The Kw at my temperature, 25 degrees, 1 times 10 to the negative 14. What is the amount of H plus that the water will self-ionize to generate? So 1e negative 14 divided by 3, as expected here in a very heavily basic solution, I would imagine that the H plus is very tiny, which it is. The X amount, the H plus that we have is into the 10 to the negative 15. And the conclusion from yesterday, whenever we have our hydroxide as bigger than the H plus, our hydroxide currently is 3 molar. Actually, the higher this gets, water will actually make sure that the H plus is even lower than this. But currently, these values, the H plus is 3.3 times 10 to the negative 15. So what I want to emphasize in that question here is this one gives us a really nice way. If you know one of them, if you know H plus, you can get OH minus or vice versa. In this case, I knew OH minus. I can use the KW expression because the solvent is always assumed to be water. We can always just calculate for the unknown. Right? In today's lesson, I want to introduce again more equilibrium constants, more KEQ. Again, only change with temperature, no units, all that's true. But I want to come back and take a look at what if I'm looking at the acids. For the acids, it's going to be Ka. This is called the acid ionization or dissociation constant. And then I'm going to notice on the table they were a little bit lazy. They didn't actually give me a column of Kb values, but we can even do a base ionization constant as well. So if we just go on our notes here, this is actually, if you're following in the workbook, 4.8 is actually referring to Ka. This is our, as I just mentioned here, it's the acid ionization constant. Pretty much if the chemical we're looking at is acidic, if it's going to donate a proton, we're going to use a subscript A. 4.9 in contrast here is going to be Kb. It basically repeats what we're going to do on the acid side. Base ionization constant, another way of saying that is base dissociation constant. Right, both of those refer to things breaking apart. Okay, so this one here is, it is basically KEQ, but we're looking mainly at picking some of the acids on the left side or picking some of the bases on the right hand side here. Let's start off with things that I'm not going to worry about Ka and Kb. And those ones there are actually going to be the things that are strong. So far for strong things, we've been saying it's 100% ionized. This one here is a one-way arrow. There is no equilibrium. So there's no sense in talking about KEQ. Well, let's try it out here. Let's say I have hydrochloric acid. Hydrochloric acid is strong acid here. So this one here breaks up 100%. It's a hydrogen salt. It breaks up to become H plus and Cl minus. That's the equation as written on the table. I can even write the complex equation. Usually when we do K and Kb, I want to really see how things actually are. So let's go from the simple equation. Let's go to the complex. Remember, for the acid side, it's like adding water to both sides. When you add water to both sides here, I see the equation. No real difference, right? HCl is now swimming in the presence of water. The only real difference is still one-way arrow. The H plus and water would have complexed together and end up forming hydronium, right? If I had asked you, well, what is the KEQ for this expression? Right? Well, KEQ is supposed to be products over reactants. It's supposed to tell me roughly when I'm at equilibrium. Well, I'm not at equilibrium, but if I reach equilibrium, is it a situation of equilibrium where I have more products or more reactants? In this case here, you'll notice it's a one-way arrow. So if I started off with a box full of HCl, it's a 1-to-1 ratio. I'm going to get a box full of H plus, a box full of Cl minus, and it's implied that the Cl minus is effectively gone. So what I have is a situation where products are humongous. This one here is big, and the reactants are essentially approaching zero. It's like no HCl's are holding hands anymore. Water has completely leveled it off. So if I divide by a number that's getting closer and closer to zero, the KEQ here, we're just going to say is very large. Right? It's approaching infinity. And so if I have a strong acid, if I look on my table again, strong acids are on the left-hand side. The strongest ones are on the top left. So these ones here are my strong acids. These ones here are all one-way arrows. I see that they just say their equilibrium constant, Ka, is going to be very large. They don't even bother with a number. Right? Infinity is not a number. Okay. So again, Ka will be much more important when we deal with weak things. Let's do a sort of parallel on the base side here. Similarly, if I have a strong base, 100% ionized, let's take the strong base here like O minus 2 and water. Right? This one here is going to form 2 hydroxide. Somehow the base was still able to form the hydroxide, even though the O2 minus didn't have a hydroxide it was holding on to. But O2 minus is a strong base. It's on the right-hand side of the table. If I try to, again, write out the KEQ expression, if I try to do KEQ, again, all I would do is I would just rename this as KB. the Kb value is supposed to be the products over the reactants in this expression here. Because of this one-way arrow, I may have started off with a bunch of oxide. This one-way arrow ends up forming all into hydroxide at a 1:2 ratio. I effectively have no more reactants and all of its products. Again, products are big, and my reactants are going to basically approach 0. So all I'm going to say is Kb is actually also going to be very large. So that's just sort of a catch-all here. We are going to look more so at Ka and Kb when it actually matters, but definitely for strong things here, it doesn't matter. So if you look at this here, on the base, we want to look on the right-hand side here. The strongest bases are the weakest conjugate acids. The strongest bases are also going to be one-way arrows. You'll notice that they didn't give us a column of Kas. They didn't give us the Kb. They gave us a Ka value. In this case here, if the acid has a really hard time coming forward, it's because the Kb value is actually very big. And I'm going to give you a link later on how do we calculate the Kb if I know the Ka of the conjugate. So I actually have a very big Kb or very small Ka for my partner. Okay, so far we started looking at, well, K anything is just the equilibrium constant, right? It's products or reactants, but things that go one way here, they're just, I don't really need to deal with them because the numbers aren't anything sensible. Much more important when we start dealing with something that's weak, okay? I will need to worry about Ka and Kb. Again, on the table, what's quoted for you here, I've given you all the acid ionization constants. The acids are only on the left-hand side, so these numbers that I look at will refer to these acids in coming forwards. That's their equilibrium constants. Later on, I will be interested in Kb. I will be interested in looking on down the right-hand side, how good are these bases coming in reverse? It's just that they did not tabulate for me. Oh, here are a bunch of Kb values. We're actually going to not need it, so we can actually calculate for it there. So you can take your pick of any acid here. Let's take our friend here, acetic acid. So I'm going to take the equation here. They give us our constant. They give us experimentally as 1.8 times 10 to the negative 5. This equation, again, on the table is simplified. So let's take our Chku, our weak acid. On the table, it just says weak acid is equilibrium. It's going to lose H plus and form acetate like that. We're not going to do Ka until it's the complex equation. Remember, on the acid side, to make the complex equation, we just did this. It's like adding water to both sides. Water is also present. So therefore, what ends up happening here is we have our Chku. It reacts with water. We're going to still be in equilibrium because we're still a weak acid. It's the left-hand side that's the weak acid. The H plus and H2O then therefore becomes hydronium, and this one is then CH3COO minus acetate. Okay. With our Bronsted acid base theory here, the Chku here has an H plus. It's going to toss the football over. That's why I know the acetic acid is acting as the acid. The person that's going to accept is going to be the water. Water is amphiprotic, but in this case, it wants to receive the football. Once the water is now holding onto the football, it's now the acidified form, the conjugate acid form, and acetate is the leftover base form. Again, just some reminders from previous lessons. We need to have 2 conjugate pairs be released when that one proton gets transferred. The conjugate pairs have to be on opposite sides because I need to have one guy willing to toss and one guy willing to receive. Because this one here is actually in equilibrium, it does now make sense to do KEQ. And again, just like we did for the base side, we're going to rename the KEQ to Ka. So the Ka is supposed to be products over reactants. My products in this case are H3O plus, multiply it by our Chku, divide it by our acetic acid all at once. Looking at the states here, these ones here are aqueous, so definitely include them. Why don't I put the water in? Water, we don't think of it as dissolved in itself. That one is a liquid. Remember, make a note to yourself. We always ignore pure liquids. In this case here, it's the only water, L, in the equation. So there we go. This actually gives us a lot of power. In part 2 of our chapter, we're actually going to use this, doing ice tables again, actually playing around with the numbers. For the time being, we just want to make sure we understand this expression. As you look at the table, great. They've actually listed for us all the Ka values. So if I look up acetic acid, the Ka value was quoted as 1.8 times 10 to the negative 5. They actually tell me that this fraction that I've alluded to here, this fraction is actually Ka 1.8 times 10 to the negative 5. So what's my conclusion here? Well, this again here, the equilibrium constant is small. Okay. Now it's sort of midway on the table. There's things that are even tinier than this. But whenever your product over reactant ratio is small, that means we actually have a situation, right? My whole fraction is tiny. That means we have not a lot of products, we have a lot as reactants. So just put some numbers to this here. Let's say I have 1 molar of the acetic acid. Unlike a strong acid, which will break off, oh great, 1 molar H plus, 1 molar acetate. In fact, the equilibrium constant is so tiny, only a small fraction, a small corner of this actually breaks off. We're looking at probably like maybe 5% actually ionizes over. Majority of it will actually stay on the side here. And that makes sense then. Reactants are favored. That's another way we can say that. Reactants are favored. Right. Because reactants are favored, we have a lot more of them. Its concentration will still be 0.997 molar or something like that. And the only fraction that went over is like 0.003 molar. Not a lot of H plus, not a lot of acetate around. Okay? So that's just introducing what Ka is. Just looking at the size of the Ka value. These are all equilibrium constants. Starting off with the strong acids, which are basically all products. Starting off with really, really big Kas here. We had our acetic acid, which is 10 to the -5, which is tiny. But as the Ka starts getting weaker and weaker, the acid has a harder and harder time actually going forwards. So all of these guys here on the left side could be acids, but as they go down, the strength of acid decreases. So one conclusion out of there here is we can say, if I have a relatively bigger Ka, means a stronger acid. Now again, what's confusing here is we're still going to be talking weak acids. We're still going to be talking, these are the ones that hit equilibrium. But of these ones here that hit equilibrium, some acids are better than other acids. Some are stronger weak acids. Okay. What I'm going to do now is I'm going to look on the base side. The base side is a little more interesting because I don't actually have a whole column of, oh, by the way, here are all the Kb values. This is looking at the base side going in reverse. This time what I'm going to do, I'm going to be really sneaky here. I'm going to look at acetate as a base, right? We're on the right-hand side, so that's the base. As a base, it's supposed to pick up a proton and then reform acetic acid. It's going to be related to this number, but this number is currently a Ka. This number currently just tells me my acetic acid is incoming forward. So what I'm going to do, base reactions I need to read right to left. Take the acetate, pick up the proton. Let's just do the sort of matchup on the right-hand side here. I'm going to take the acetic acid. I'm going to write it as a reactant. The simple equation just says, as a bronze tellurium base, it's supposed to pick up a proton. It's still in that weak section, so it's in equilibrium. It ends up reforming our Chiku, acetic acid. Again, don't try to do an equilibrium constant until you have the complex form. This was how it was written on the table. This one here was actually simplified. How do I, on the base side, switch it to the complex form? Remember, it's almost like what you're doing is you're adding hydroxide to both sides here. And what's going to end up happening here is we're going to have our acetate, CH3COO minus. The H plus and the OH minus are going to form water. And this is going to end up creating our acetic acid, reforming that is reversible, and then leaving you with hydroxide. As I would expect, a base is supposed to give you hydroxide. Now, we had seen this sort of inverse relationship. Well, if I lose H+, that's similar to gaining hydroxide. It's just a little bit more clear, especially for ice tables later on, if I actually have hydroxide directly in the expression, which we will always have for the complex. Remember, just a little bit more background of this here. Effectively, what's happening here is we have acetate in solution, CH3COO minus. It is going to pick up a proton, but like we said, the amount of protons in solution at 25 degrees is really, really low. The Kw is actually really tiny. The acetate is not going to find H+ as easily. In fact, what we can do is we can think of, instead of the acetate just picking up an H+ and forming acetic acid, that can happen, no problem. But what we're going to imagine here is it's actually water that's much more plentiful, H2O. Water has the football. Water is going to give the acetic acid that football. So the football goes from H+ over to acetic acid. The acetic acid will then still form our Chiku. It's actually our water that's actually going to drop behind a hydroxide. Okay, so that's what that says there. Because there's not a lot of H+ in solution, the complex form not only allows me to see the hydroxide as an individual term, it actually shows me acetate actually stole a proton from water. Now that I have the complex equation, again, I can do a KEQ. I'm going to call it Kb because this one here is a base equation. Right, that's a nice hint. Ka for acid, Kb for base. It's essentially products of reactants. So this one here is going to be our acetic acid, Chiku, times it by the hydroxide, divided by the acetate ion. Right? So again, if you know this expression here, you would know the value. Again, on our part 2 of this chapter here, we're going to use ice tables. We're actually going to need to do a lot of the math. Okay, but there we go. We can actually find the Kb value. What I want to show you based on this comparison here is, wait a second. Look at Ka. It has sort of acetic acid, acetate kind of terms here. Kb also has these terms here. I'm going to do somewhat crazy math here. I want you to consider what happens. So we've already talked about what is Ka, what's Kb. I want you to consider, what if I took Ka, right now here this was for acetic acid, right? That was the acid partner. What if I tried to multiply the Kb for my partner, so acetate? Okay. So effectively what I'm going to do is I'm going to take this left-hand side here. The Ka was, we had hydronium. We multiplied it by acetate, divided by acetic acid. That was the Ka expression that we did earlier. Let's multiply it by this Kb expression. Kb is also acetic acid, multiplied by hydroxide, divided by acetate. Seems kind of crazy. Why am I doing this? Well, because they have very similar terms. Oh, look. The acetate actually kills off the acetate. Acetic acid kills off the acetate. This one here will leave us with just plain old H3O plus multiplied by OH minus. Do you recognize that? Right. Oh, wait a second. This is what we did yesterday. If I have H plus times hydroxide, this part here actually equals to Kw. Right? So we did some sort of crazy math here. Why bother Ka times Kb here? It's to give you this conclusion here. In fact, I don't need to tabulate a bunch of Kws for you, Kb's for you, because Kw is actually what's left behind. Ka of the conjugate acid multiplied by Kb of the conjugate base. So another relationship for you to memorize there. We know the Kw value. We know it's 1 times 10 to the negative 14. In fact, more to the point here, because I have all these Kas listed, anytime I want to know the value going the opposite way, my base incoming reverse, I just take Kw, 1 times 10 to the negative 14, and I divide this number, and I've now figured out the base part going backwards. Right? So let's actually try finding it here. What if I was interested in what is the Kb of acetate after all? What I'm going to do is I'm going to take Kw divided by the Ka of my partner, acetic acid. So I'm going to take 1.0 times 10 to the negative 14. The Ka value was listed for me on the table, this 1.8 times 10 to the negative 5 number. That was talking Ka, that was going in the forward direction. That was my acid coming forward. I'm going to divide out this 1.8 times 10 to the negative 14. 1.8 times 10 to the negative 4. No, 10 to the negative 5. Right, just look it up on the table. And therefore what I have is 1e negative 14 divided by 1.8e negative 5. This gives me here 5.6 times 10 to the negative 10. Okay, let me write this in words for you here. This Ka value, so Ka on table, describes how good our acetic acid is an acid. Okay. What I found here by going Kw divided by Ka, this Kb is not on the table. The Kb describes how good my acetate ion, notice it's the conjugate, my acetate is a base. So people generally memorize this, yeah, Ka times Kb equals Kw. You have to be careful. It's not Ka of the same chemical. These ones here have to be partners of each other. They have to be involved in the same expression. So case in point here, let's see, can you calculate for me? Calculate the Kb value for oxalate. Okay, so calculate the Kb for this expression. Let's go back to our table and let's look for it. Wait, this one here has a hydrogen, this one here has a negative. It could be amphiprotic. I would expect to see this Hc2O4 minus on two sides of the table. So let's find it here. Okay, Hc2O4 minus as an acid, its Ka constant is 6.4 times 10 to the negative 5. That's how good it is at coming forwards. So Ka of Hc2O4 minus is 6.4 times 10 to the negative 5. Is that the Ka I divide? Or I also find Hc2O4 minus up on the top of the table here. So I have Hc2O4 minus, and I have a Ka value here. What does this 5.9 number tell you? that's actually the Ka. It's a Ka, so it's the acid. That's actually telling you how good my H2C2O4 is actually at coming forwards. So Ka, this number here, H2C2O4, that one there is actually 5.9 times 10 to the negative 2. I knew my expression. My expression was supposed to be, well, yeah. Kw is equal to Ka times Kb, so therefore I can rearrange it. Good. Kb is equal to Kw divided by Ka. The question is, which Ka am I supposed to divide? The Ka of my partner or the Ka of me, myself? Remember when we derived it, it's pretty much the base. When you find it, I want to look for it on the base side, and the Ka I'm actually going to divide is actually the Ka of my partner. That should make sense to you, because if this number here is very large, right, I'm very high up on the table. If I go a constant divided by a big number, I'm going to get a small number. If this is really good at coming forwards, I'm not so good at going in reverse. If the Ka value were much tinier, if it was really having trouble coming forwards, I'm going to have a much larger Kb and going in reverse. When you divide by Ka, it's dividing by Ka of the partner, not necessarily your own Ka. If you did Kw divided by this number instead, you would have found the Kb of the oxalate ion and coming in reverse. So long story short, if you're looking for a Kb value, look for your chemical on the base side, and then you're going to go Kw divided by that Ka. The Ka is actually of your partner. So this one here is 5.9 times 10 to the negative 2. Let's just work through that there. So the Kb, this is the one that I want. The Kb of my hydrogen oxalate is equal to Kw divided by Ka of my partner. Right? We're always in pairs. So therefore, 1.0 times 10 to the negative 14 divided by this hydrogen oxalate here. This one here is relatively big. So 5.9 times 10 to the negative 2. Still weak though. So 1e negative 14 divided by 5.9e negative 2. And this gives me here 1.7 times 10 to the negative 13. All right. And as I alluded to here, the larger the Ka value, the smaller the Kb value is going to be. They're going to be inversely related so that they can always multiply to give 1 times 10 to the negative 14. So we're starting to see this 1 times 10 to the negative 14 as a really important number. It gave us a nice mathematical link between H plus and OH minus. More on this tomorrow. And also it gave us a nice link. I don't need to tabulate for you a bunch of Kb values, because you can just look for it on the base side and go Kw over my partner to find the Kb value. All right. I'm just going to finish off with one last little setup here. Just another little spin-off. What can I do with these Ks and Kbs here? I want you to consider a new equation. Consider the equation between just two random acids, HCO3 minus and H2PO4 minus. Okay. I'm going to ask you sort of similar to what we did before. We had hinted at this in yesterday's question as well, but let's just try it out again. Both of these ones here have an H, and both of these ones here have a charge. Both could be amphiprotic. What I'm going to do is I'm going to compare. I'm going to write down for you here. Compare the acid strengths to determine who donates the proton. Right, both of them are willing to toss a football, and I'm just looking at acid strengths because on my table I'm given Ka values. Let's look for these two compounds here, HCO3 minus and dihydrogen phosphate. HCO3 minus is down here, dihydrogen phosphate, H2PO4. Cancel some of this. H2PO4 is slightly higher than it. I looked for it on the acid side. Remember, the strength of the acid increases as I go higher up on the chart. H2PO4 minus is a stronger acid. Its constant is 10 to the negative 8, whereas HCO3 minus is constant is 10 to the negative 11. So while both of them could be acids, the H2PO4 does its job better. So let's just write this down here. So the Ka of HCO3 minus, just copy down the numbers from earlier. The Ka of this guy here is 5.6 times 10 to the negative 11. That was not as big. The Ka of my phosphoric acid was a little bit higher. This one was 6.2 times 10 to the negative 8. Because, so since the Ka for my dihydrogen phosphate is larger than the Ka for HCO3, this guy gets to be the acid. This guy gets to toss a football over. So it wasn't immediately clear. It wasn't like, oh, it's obvious which side is the base. Now what we've decided is, yep, this is going to be the acid. This is going to be the base. So what's going to happen to the HCO3 minus? It's going to go up by an H, go up by a charge, H2CO3, and then the H2PO4 minus is going to go down by an H, so it's now going to be HPO4 minus, go down by a charge, negative 2. Always one proton transfers. It's just a matter of who has the football now. Right? as you started alluding to in yesterday's lesson here, I've actually ended up creating the conjugate acid of HCO3 minus. It's now the conjugate base of HPO4 minus 2. Even though H2PO4 minus won out as an acid, I now need to fight, well, there's another acid to fight against now. H2CO3 likewise has a Ka constant. Let's compare the acid strengths. So we did it once just to figure out what the reaction is going to be. I want you to compare it again, but this time, when we compare acid strengths, we're going to determine which side is favored. Again, similarly, I could have compared basic strengths. It's just that I don't have Kb values tabulated for me, so I'm just going to prefer to compare acid strengths. So now I fought H2PO4 minus against HCO3 minus. Let's fight it against H2CO3. So H2CO3, look for it on the acid side. H2CO3 right here. So carbonic acid, it has a Ka constant of 4.3 times 10 to the negative 7. It was actually better than the other two. Let's just take that number down. So 4.3 times 10 to the negative 7. Let's go down here. Ka for this new acid, it wasn't in existence before we donated the proton, but after we predicted this one here, the Ka here was that 4.3 times 10 to the negative 7 number. And now look at the Ka, since the Ka of the new acid that I created, H2CO3, is bigger, is stronger than the Ka even of the H2PO4. This time it's not to determine which way the proton goes. This way it's saying, here's my volleyball game, which one's the stronger team? I actually have the stronger team on the product side. Normally, naturally, in words, I say, oh, they're stronger, they're favored, right? But remember, for favored, it actually means which one do I have more of at equilibrium. If I have the stronger acid on the product side, and if they're doing their job better, they're going to hit the volleyball more to the left-hand side more often. At the end of the day, I'm actually going to have more reactants than products. That's a little bit strange in wording. So since Ka is H2CO3 is bigger than Ka H2PO4 minus, we can say here the stronger acid will push the equilibrium to the left, and therefore, even though we will end up in equilibrium, we're going to end up having this balance here. We're going to have a balance where we use the phrase, reactants are favored. They're not favored because they're the side with the stronger acid. In fact, they're the side with the weaker acid. But when we say it's favored, it just means that there's more reactants. The concentration of that one is actually higher at equilibrium. Even though we're at this balanced state here, we have way more of the left side than the right side. Each of these acids by themselves, right, if you look at them individually, each of these acids here had very small Kas. So they were already reactants were favored. We're actually doing a little bit more broad scale here. We're actually not just having one acid solution, we're actually comparing an equilibrium between two of these reactants here. Right? Again, I'm going to just show you a little bit of crazy math here. That already gives you the answer. I know I have more reactants at equilibrium. Could you comment on what KEQ is? Why do I have to talk about KEQ? Well, each of these guys here have Kas, they have Kbs, they have all individual constants here. But now for my really, really big equilibrium, for my very last volleyball game, we have a situation that there's more reactants. So KEQ is supposed to be products over reactants. If I have a situation where I have way more reactants than products, so therefore my KEQ is very tiny. KEQ, you can say, is much less than 1. Just for completeness sake here, you don't really need to do this last part. I can actually calculate what the KEQ is. I expected it was very tiny. What if, so just think, what if what I did is I ended up going Ka of H2PO4 minus, right? So that's the acid on the reactant side. So that's 6.2 times 10 to the negative 8. What if I did that one divided by the Ka of the carbonic acid that I just created, H2CO3? Again, you're going to be like, well, why did I do this? Again, we'll mathematically work it out and we'll see what it gives us here. This one here is the Ka of the acid on the reactant side. The H2CO3 currently is on the product side. This is going to be a little more confusing because I didn't actually write out these equations. I was dealing already with the overall equilibrium. I didn't write out this guy, when it tosses a proton over, what does this guy end up being? What does this guy end up being? Let me just write those out for you directly here. If you just focus on the H2PO4, the H2PO4 minus in the presence of water ends up forming HPO4 minus and H3O plus. How come I didn't see an H3O plus in this big equation? Is because the H3O plus actually got picked up by the hydrogen carbonate. But nonetheless here, let's just work that out. HPO4 minus times H3O plus divided by our dihydrogen phosphate. In a similar fashion here, I sort of shortcutted this part here. H2CO3 in the presence of water, it also donates a football, becomes HCO3 minus, H3O plus. The Ka value, again, looks crazy. HCO3 minus times it by H3O plus all over H2CO3. Right? Now that looks horrible. Well, I have a fraction divided by a fraction. I can actually think of taking it multiplied by the reciprocal. You don't really have to do this last step here. I just want to show you one last relationship. If I divide by a fraction, it's like multiplying by the reciprocal. If I multiply this up here, I get H2CO3 all over HCO3 minus and H3O plus. This time, not as many things cancel out. This time, all you see is actually, it's just the hydroniums cancel out. Well, what's so nice about this expression? I have HPO4 minus times H2CO3. It still looks horrendous. If you look at this one here, H2PO4 minus multiplied by HCO3 minus, compare it to our big equation here. Our big equation, if I did a products over reactants for this expression, my KEQ would have been, well, H2CO3 times HPO4 minus 2 all over HCO3 minus H2PO4 minus, and that is an exact match of what we just found. So what that tells you here is, not only can you just predict for me, yeah, the KEQ is small, the K is going to be much, much less than 1, you can actually figure out what is the actual value by taking these two values as is. The Ka for the H2PO4 minus, let me just requote for you here, the Ka on the reactant side was 6.2 times 10 to the negative 8, divided by that on the product side, 4.3 times 10 to the negative 7. We actually have a mathematical way of actually calculating the exact number. I already decided it was tiny, but here is just more information. My KEQ is 0.144, which is consistent with the fact that I said reactants are favored, the K is less than 1. You don't really need to do this last part. That part here is a little bit more complicated, but you will need to get at least up to this point here. If you know we have the stronger acid, they do the job better. They hit the volleyball over to the other side more often, so it's the reactant side that are favored. Since KEQ is products over reactants, the K is much smaller than 1. Okay, so practice through a few problems there, and we'll pick it up from there tomorrow. Thanks, guys.